Hello students, welcome to another session of All Force e-learning program. Now in this session, we shall take up the applications of the electric field due to a charged spherical shell. The applications of the electric field due to a charged spherical shell. Applications. The various things that are based on which based on this topic, what are the various questions he will be asking. We will take up the things there. So we have evaluated, in the previous session, we have evaluated the expression for the electric field due to a hollow charged sphere at an outside point. So when I was considering a hollow sphere, this is a hollow charged sphere, hollow sphere like this, charge Q, its radius is R, center O, like this. So we have evaluated a formula for the outside point. At the outside point here, at a distance R, the electric field at a distance R here at point P, we have evaluated the formula for the electric field at the outside point. It's 1 by 4 pi epsilon naught, it's Q by R square. Now the question is the case 2, the special case. When we consider case 2, now in this one, now what will be the electric field if the point is on the surface of the sphere? The point is on the surface of the sphere. So expression for the electric field intensity when the point is on the surface of the sphere. Now let us evaluate, let us find the formula for the electric field, right, for the electric field at any point on the outside surface point of the hollow sphere, outer surface of the hollow sphere. Now consider a point P on the outer surface of the hollow sphere. Now the distance of the point small r is same as the radius of the sphere, because the radius is from distance from center to circumference, surface, center to surface. Our point is also on the surface. Now the distance of the point small r is capital R. To go according to the method Gaussian this thing, first imagine a Gaussian surface. Imagine a Gaussian surface over the surface close to the surface of the hollow sphere. So these dotted lines represent the Gaussian surface. So imagine a Gaussian surface, first step. Right, I have imagined it symmetrical to it, concentric to the sphere, charged sphere. Now the electric lines of force from the charged sphere along the outward, they are along the outward normal. So the electric field direction is E. If I imagine a small area element, even the direction for that area element is also in the outward normal. Both are parallel. So the small flux through the element we have derived earlier, the small flux through it d phi is simply E dot ds, and since both are in same direction, I can write it as E ds, theta 0, cos 0 1, so E ds. Then if I imagine such area elements throughout, the total flux emerging from the Gaussian surface will be, it is E into the total surface area. E is a constant, E is same at all the points because all are equidistant from the center, right? So the total surface area is 4 pi. Now small r is capital R, it is 4 pi r square. The total flux emerging from the surface of the hollow sphere, our Gaussian surface is also on the surface only. So therefore the total flux is E into 4 pi r square. Now according to Gauss law, we know that total flux is charge enclosed inside by epsilon naught. So charge inside that Gaussian surface, because we have imagined the Gaussian surface over the surface of it. So the charge is inside. So therefore it is Q by epsilon naught. So equating both, I get the electric field is equal to electric field E into 4 pi r square is Q by epsilon naught cross multiplying. E is equal to 1 by 4 pi r square epsilon naught Q. So the electric field due to the hollow sphere on the surface point, at any point on the surface, right, the surface point, the electric field E is equal to 1 by 4 pi epsilon naught, it's Q by r square it is. right? So this is the formula. Magnitude for the electric field, well, it is nothing but we have deduced the electric field at the outside point. We have derived the formula as q by small r square. Now small r is equal to capital R because the point is on the surface, so I am putting small r as capital R. This is capital R. So the electric field magnitude is 1 by 4 pi epsilon naught q by r square. Okay, now in vector form, suppose if it is in vector form, then the electric field on the surface E bar at the surface point, it is 1 by 4 pi epsilon naught q by r square times a vector can be defined as, it is equal to the magnitude of the vector times the radius vector, the unit vector in that direction. Now our unit vector is along the radius vector, so along the radius vector is r cap, right? So it is capital R cap. So the vectorially I can write this as 1 by 4 pi epsilon naught, so it's q by r square. R cap is r bar by mod r, but mod r is magnitude of capital R, small r is same as capital R, so I can write as capital R. So the electric field on the surface is 1 by 4 pi epsilon naught q by r cube, it is r cap, sorry, r bar. Vectorially 1 by 4 epsilon q by r cube, r bar the radius vector, then the radius vector is again equal to same as this, right? Vectorially I can represent in this form. Now if the electric field is now asked in terms of surface charge density, instead of giving you charge, suppose if he gives you surface charge density sigma, instead of q he has given you surface charge density sigma. Well, we know surface charge density is charge per unit area, so charge is q by area is 4 pi r square, cross multiplying, now the q will be sigma times 4 pi r square. Now substituting here, the magnitude of the electric field on the surface is 1 by 4 pi epsilon naught q, q is sigma into 4 pi r square by r square, it is r square. So 4 pi cancel, even r square is common, cancel. So electric field on the surface is sigma by epsilon naught. Electric field at any point on the surface is a constant. So it is surface, because the charge distribution is uniform, the surface charge density is a constant. Of course this is electrical permittivity of free space, even this is a constant, so electric field is also. So please look at this expression. This expression is surface charge density by epsilon naught. It is the expression for the electric field intensity due to an infinite sheet. An infinite sheet of surface charge density sigma at a very close nearer point. For a conducting sheet, it is sigma by epsilon naught. So by this can be even deduced in this form also. In the previous episode, when we were evaluating the expression for the electric field intensity due to an infinite sheet. Now if I consider this charged sphere, let this be a charged sphere like this of surface charge density sigma. Now I have imagined a Gaussian surface over it like this. I am imagining Gaussian surface. Now instead of total Gaussian surface, right, I have to find the electric field at a nearer point, a very close point here. Now let me imagine a Gaussian surface like this. A Gaussian surface in the form of a cylindrical Gaussian surface at a very close point. To make it visible for you, I am putting it like this, but the point is very close to it. So I am imagining a Gaussian surface. You compare this with the electric field where we have derived for the infinite sheet. So this is the outside point P where I have to find out, well, just very close to it, very close to it. Right? The distance, I was telling you, the distance of the point P is very negligible when compared to the size of the sheet. So the radius of the sphere is now big, but the distance of this point is very small. This is in meters, this is in millimeters. Then now imagine a cylindrical Gaussian surface like this, symmetrical to that surface, symmetrical to this charged this thing, right? Symmetrical to it. Let this area of this circular cap be A. Area of this circular cap is also A, right? Now the direction of the electric lines of force are along outward normal, even outward normal like this, right? Well, inside there is no field. Inside this, it is a hollow sphere. There is no charge inside. Inside charge 0, no electric lines of force. So the field inside is also 0. So here over this cap, over this outside cap of the cylinder outside the surface, the electric field is E and the area element is A. Over this inside cap, circular cap, area is A, but there are no lines of force, no electric field, no lines of force exist. Electric lines of force are along outward normal, emerging from the surface, going to infinity. So therefore there is only field outside. So if I consider this small area element, the flux through this, now this curved part of the cylinder, suppose if I consider a cylinder like this, a small cylindrical surface like this, right? This is the circular cap outside, this is the circular cap inside. This circular cap, here the electric field is E, here the electric field is E in this direction, E. The area of this cap is A, right? And here the area is A, but there are no lines of force inside. Inside, no lines of force, no electric field. E is equal to 0. Electric field is equal to 0. So therefore no flux here. Now calculating the total flux, when I calculate the total flux, the flux through the Gaussian surface, so flux through the total Gaussian surface is flux through this circular cap, flux through this circular cap, flux through the curved part. Now flux through this circular cap, the outward circular cap, the flux is phi is EA. Well, our flux with respect to this circular cap, here there is no field, area element is existing, but there are no lines of force. So here the flux due to this is 0. And over the curved part, the lines of force are like this, the lines of force are parallel to the curved part. This curved part of the cylinder, this cylinder, curved part, this is a curved part. The lines of force are parallel. Anywhere the lines of force will be parallel to it. So whenever, I was telling you in Gauss law, whenever the lines of force are parallel to the surface, the lines of force neither get into the surface nor emerge. No entering flux, no outward flux, no inward flux, no outward flux. So the flux is 0. So with respect to this curved surface, flux is equal to 0. So the total flux through this Gaussian surface is E into A. But we know according to Gauss law, the total flux is charge enclosed inside by the surface charge density, by epsilon naught. But we know surface charge density sigma. So for this small area, charge inside this Gaussian surface, it is Q by A. So cross multiplying, Q inside is sigma A. Putting it here, EA is equal to sigma A by epsilon. So E is equal to sigma by epsilon naught. It is same as this. So here I have evaluated this by considering it as a hollow sphere, imagining a Gaussian surface over the hollow sphere, and by considering all that, manipulating the things, I got this. Now the same thing can be evaluated by considering it as a sheet. So when he is asked you to find the electric field strength on the surface point, or a point very close to the surface. So this is, suppose, imagine this is a sphere. Imagine this is a round sphere like this. At a very close point here, with respect to this close point, this behaves as a plane sheet, an infinite plane sheet. Even though it is a round thing, at this point it behaves like a plane sheet. So considering this as a plane sheet, infinite plane sheet, with respect to the close nearer point, you can derive this. So the electric field intensity is sigma by epsilon, same as this. A very beautiful correlation, between this and this. So for a nearer point on the surface, you can imagine that even though it is a sphere, it's a sphere like this. At the nearer point, at any close point, this behaves as an infinite charge plane sheet. So for that, the electric field is E, right? And since it is a conducting this thing, the charge exists only on the surface inside. It is a hollow sphere. No field inside, no charge inside, no field inside. So the flux through the inner part of the Gaussian surface is 0. So there is no flux here. And through the curved part, no flux. There is flux only coming from this outer circular cap. So EA is charged by epsilon naught. Charge inside is sigma into A, cancelling this. A very good correlation between these two. A very good point to remember. Okay, right. electric field on the surface point of a sphere, electric field at any surface point of the sphere for a charged sphere like this. If I consider a charged sphere of charge q, on the surface point the electric field is 1 by 4 pi epsilon naught q by r square. Even this is also, you please understand. Suppose if I consider a point charge capital Q at a distance capital R from it, imagine a point charge capital Q, a point charge capital Q at a distance capital R from it, the electric field is 1 by 4 pi epsilon naught q by r square. Now comparing this with this, right, the electric field due to a point charge of same magnitude at same distance is same as the electric field due to a hollow sphere on the surface point. In the sense, comparing these two, right, correlating these two, you can understand that this charged hollow sphere, the charged hollow sphere of charge q which is existing on the surface, behaves as if all the charge is concentrated at its center q. So this hollow sphere charge q charged on the surface uniformly, right, then the electric field at this point, it is same as a point charge at the center and R. So the charged hollow sphere which is charged uniformly behaves as if all the charge is concentrated at its center here like this, right, all the charge is concentrated at the center like this, and you can evaluate it as a point charge. This is again the other form of shell theorem. So whenever you consider a hollow sphere, then you can imagine all the charge on the sphere to be concentrated at the center of charge. All the charge is concentrated at center of charge. So considering it as a point charge, all the charge is concentrated at one point, so it behaves as a point charge. Considering it as a point charge, you can evaluate the things, any electrical parameter regarding this. This is again a very important point, right? Now, so while evaluating the electric field for the surface point, I have now considered this as a, when I take a point very close to it, then with respect to this point, this behaves as an infinite sheet, right? Suppose if I consider a plane sheet, if I consider a plane sheet like this, when it is far away, it may appear to be small, but when I put it very close here at this point, this appears to be a big sheet, an infinite sheet. So with respect to a close point, this surface appears to be an infinite sheet. So it is like an infinite charged sheet. Of course, the sphere, a sphere is this sphere is going, it's continuous here. I am taking this small area element, this. So at the close point, so you can imagine this as a charged conducting charged sheet like this. Now at a close point here, now I have to evaluate the electric field. Imagine a Gaussian surface like this, symmetrical to the charge distribution, right? A cylindrical Gaussian surface like this, right? Symmetrical to the charge distribution. The outer cap, the point P lies on the outer cap. I imagine the Gaussian surface such that the circular part of this Gaussian surface passes to the point P. It's a cylindrical Gaussian surface, right? This cylinder has two circular caps and the curved part. Well, so here on this point P lies on this circular part of the Gaussian surface. The electric lines of force are outward normal, emerging normally away from the surface, the electric field. This circular cap also has area A in the same direction, right? So therefore, the small flux through this circular cap, this is, let's suppose this is surface 1, this is surface 2, and this current surface is surface 3. Flux through surface 1 is E into the area. Well, it is area is A at all the points, the electric field is same, so it is A, very close point. Now flux 2 to surface 2, phi 2. Now this is inside that conducting sheet. You know, inside the conductor there exists no charge. Charge exists only on the surface. For a conducting sheet, there is no charge inside. So the charge inside the conducting is 0. So when charge is 0, there exists no lines of force. When there are no lines of force, there is no field. So the field here E is 0. So the flux on the second, this circular cap, EA. E is 0. So the flux through the second part is 0. Now third, the curved part. When the electric lines of force are parallel to the curved part. So I was telling you, whenever the field is parallel to the surface, parallel, grazing of the surface, their lines of force neither go inside nor they emerge. No entering flux, no emerging flux. So flux through the third part, phi 3 is also 0. So total flux through this Gaussian surface is phi 1 plus phi 2 plus phi 3. But phi 2, phi 3 both are 0. So the total flux is E. Now according to Gauss law, we know the flux from the surface, Gaussian surface, the total flux from the Gaussian surface is charge inside by epsilon naught. Now the charge, this area, the area of the part which I have considered on the surface is A. So surface charge density sigma, it's Q by A. So cross multiplying Q is sigma A. So here it is sigma A by epsilon naught. So it's sigma A by epsilon naught according to Gauss law, equating flux and Gauss law. So A cancelled, electric field is sigma by epsilon. So for a conducting sheet, a conducting infinite long conducting sheet, then the electric field at any close point, the distance of the point is negligible when compared to size of the sheet. Then the electric field due to the conducting charged sheet, infinite sheet, E is sigma by epsilon. Electric field due to a conducting charged sheet, E is sigma by epsilon. A very good important point with respect to the entrance examination, very important thing to understand. You see, this I have evaluated imagining from this. So this understanding is very important, very much required. Sorry. Now, third case, case 3, let us take up the third application, third case. Now we are asked to find the electric field due to a charged sheet. Electric field due to a hollow charged sphere or a spherical shell at a point, at an inside point. Consider a charged spherical shell, right? A charged spherical shell of charge Q uniformly distributed on the outer surface of the sphere, right? On the outer surface. Let the radius of the center be O and the radius is capital R. Now we are asked to find the electric field at any inside point. Let an inside point P at a distance small r. Now here we are asked to find the electric field at an inside point of a hollow charged sphere. Now the method, let us go by the method. First step, imagine a Gaussian surface. The Gaussian surface should be symmetrical to the charge distribution. So it is a sphere. I am imagining a spherical Gaussian surface like this. Spherical Gaussian surface concentric to the sphere. Spherical Gaussian surface concentric to the sphere then. So at point P here, we have to find the electric field. Let the electric field at that point be E. Electric field be E. Then considering the small area element, the small flux is E dot ds or d phi is equal to E ds. But equating this according to Gauss law, the total flux is equal to E ds. But we know according to Gauss law, the total flux is charge enclosed inside by epsilon naught. So E into surface area S is charge inside by epsilon naught. But you know, for a hollow sphere, there is no matter inside and there is no charge existing inside. There is no charge existing inside. Hollow it is. Charge inside is 0. So inside the Gaussian surface, the charge is 0. Charge 0, hence there are no lines of force. When there are no lines of force, there is no electric field. So therefore charge inside is 0. So the electric field at any inside point is 0. So for a hollow sphere charged uniformly over the surface, the electric field inside the sphere is 0. A very important point. There exists no electric field inside a charged hollow sphere, right? For a hollow sphere inside there is no matter, you know, charge is always associated with matter. Charge is always associated with mass. For charge to exist, there should exist mass. But it is hollow, there is no matter inside. So there exists no charge inside. When there is no charge, no lines of force. When there is no line of force, no field. So the field is 0. Right? Well, the lines of force from the surface, the lines of force which are emerging from the surface, they emerge along the outward normal. For the positive charge, the lines of force are away. they extend for the positive charge lines of force, they are diverging away from the surface to infinity. If it is negative charge, the lines of force converge from infinity onto the surface, they stop over the surface. No lines of force do not enter inside because there is no field inside, no charge inside. Right? Even if it is inward flux, suppose even if I take negative charge, inward flux, the lines of force will approach the surface and they stop over the surface. No line of force exists inside. So no charge inside, no field inside, no lines of force inside. So the electric field at inside point is equal to 0. Right? Very well. These are the electric fields for the charged sphere. So putting all the things together, when I consider a charged sphere of charge q of radius r, then the electric field at various points. At infinity, we know, at infinity the electric field due to any charge is 0 because the distance is so high that the field becomes so negligible. The field at outside point at infinity is 0. At any outside point P at a distance r, here the electric field at an outside point, it's 1 by 4 pi epsilon naught charge on the sphere q by r square. At any point on the surface, the electric field at the surface point, right, it is 1 by 4 pi epsilon naught q by capital R. Now the distance of the point is capital R, so it is q by r capital R square. And electric field at any inside point, at an inside point there is no charge inside, no field inside, no lines of force inside, so the electric field at any inside point is 0. Now what is the electric field at the center? When inside point is 0, then the center also exists inside, the electric field at the center is also 0. Same thing, if the same formulas are to be represented in terms of surface charge density, then it is sigma into 4 pi r square, 4 pi r square cancel. It is sigma by epsilon naught. Here it is sigma into capital R square by epsilon naught small r square. Magnitude wise, because the charge q is sigma into 4 pi, charge is q is equal to 4 pi r square sigma. Right, so therefore 4 pi r square sigma, in the denominator there is 4 pi, cancel, capital R square by small r square. At outside point, on the surface point, at infinity field is 0. Electric field due to any charge at infinite point 0. At infinity there exists, the lines of force become so diverging that there is no influence of the charge there. So at infinity field is 0. At outside point q by r square. On the surface point q by capital R square. At any inside point it is 0. So suppose if I picturize this in the form of a graph, if I want to represent this graphically, so the variation of the electric field with the distance smaller. The graphical representation of the electric field, how does the electric field vary? For a hollow charged sphere, for a charged spherical shell, right? Then the representation is like this. At this center there is no electric field, so electric field is 0. Right? The electric field at the center is 0 like this. At all the points at the inside point the electric field is 0. So at all the points the electric field is 0. I am representing by this yellow line. At all the points the electric field is 0. At all the points it is 0. But on the surface point here, at a point at r capital R equal to r, then the electric field suddenly starts from this point, right? So here it starts. The electric field at all the points is 0. So here at a distance small r equal to capital R, small r is equal to capital R here on the surface point, the electric field is here and this is maximum. This is the electric field on the surface, that is 4 pi epsilon naught capital Q by r square, the maximum electric field for a hollow sphere, right? So it is on the highest electric field exists on the surface. At any nearer point close to the surface, the electric field is maximum. And outside the field, the electric field is inversely proportional to square of the distance. It obeys inverse square law. So the curve representing inverse square law, it is a steep curve like this. Well, at infinity the electric field is 0. So this curve will touch the axis, this axis at infinity. So at an outside point, the electric field is a steep curve like this, showing inverse square law, right? From center to surface, electric field is 0. On the surface, the electric field is maximum. What is the maximum field for a hollow sphere? On the surface, charged hollow sphere on surface, it is equal to 1 by 4 epsilon q by capital R square, right? Then outside point it varies inversely, so it is an inverse square law. So a steep curve like this, and it touches this, it is like a asymptote, it will touch the x-axis at infinity, right? So this is the graphical variation of the electric field with the distance, right? Thank you.